PE becomes the KE becomes the PE, all through work. So let's look at the conservation of energy. In a closed system, energy will always be conserved. It can't be created or destroyed. It seems to be violated sometimes by the concept of waste energy, but we have to include waste energy, which we're going to call Q. You might remember from chemistry, Q equals mc delta T. So the energy total formula is the sum of the kinetic energy and the potential energy and the wasted energy, Q. Let's look at a system like this cliff diver. A cliff diver dives off a cliff. He climbs to a height of 50 meters above the water. How much PE does he gain? Well, mg delta H. Since we have his weight in newtons, that's already mg, we must gain 25,000 joules of potential energy. So how much kinetic energy must he have when he falls? Well, he must gain that 25,000 joules. In other words, the PE at the top must equal the KE at the bottom. What's his speed when he hits the water? Well, from there we can use the kinetic energy formula to find his velocity, 31.3 meters per second. KE equals 1/2 mv squared. Let's take a closer look at our cliff diver here. Here he is at the top, relative to the water. He's falling. Ah, there's a shark! Fortunately, I can stop the laws of physics here. And notice that halfway down, half of the energy is PE, but half of it's been converted to KE. The kinetic energy principle stays here that all the PE becomes KE. So he gets to the bottom, he will hit the water with the velocity. Hopefully there won't be any more sharks. No, there's a fast shark. And notice all the energy is KE. Let's try a skier. How does the energy work in this particular kind of system? So in this system, note that at the top of the hill, all he has is PE. Look at the bar graph. All that PE becomes KE as he slides down the hill. When he gets to the bottom, the unpacked snow has friction, and so the friction does work on the skier, converting it directly to heat. That's why he loses kinetic energy and eventually comes to rest. That's friction doing work on the system. But again, the total energy is conserved. Here's a roller coaster. If we have a 1,700 kilogram roller coaster operating on a frictionless track, moving at 5 meters per second as it passes over the top of the hill, what's the roller coaster's PE at the height, at the maximum height? Well, if it's 35 meters above the ground, we can get that as 583,695 joules. So what's its KE? 1/2 mv squared. We got 21,250 joules of energy. So what's the total energy? Well, it must be equal at the bottom of the hill. We're not losing any to friction. The sum of all of them, 604,945 joules. From there, we can find the speed at the bottom of the hill using the kinetic energy formula. 1/2 mv squared, 26.68 meters per second. Pretty fast. Here again is the roller coaster system. Just looked at it in an animation. Notice the bar graphs. PE becomes KE. It bounces back and forth between some of the points. At some points, it's PE max. Some points, it's KE max. And at some points, it's some PE and some KE. Notice here in the loops. It's KE max at the bottom of the loop, and then it becomes PE and becomes back to KE as it goes around. Let's try a spring toy system. Here we have a spring toy, like the little popper things. We have a spring constant of 12 newtons per meter, and we compress it 0.02 meters. So the potential energy stored in that spring, 1/2 kx squared, is equal to 0.0024 joules of energy. So what happens when the PE is allowed to pop up? It becomes kinetic energy at first. The toy begins to lift off from the ground. But as you recall, in a gravity field, it will come down to rest at some point high in the gravity field. At that point, it's at its potential energy max, 0.0122 meters. Last example, here's a pendulum. Pendulum swings back and forth, back and forth. Where is the PE max? Well, the PE max is at the ends of the swings when the pendulum comes to rest. Where is the PE at minimum? Well, at the bottom, where it's moving fastest, there's very little potential. We can set the PE 0 there. So where is the KE at a minimum? Well, at the two ends, because it reaches rest for a brief moment of time, therefore no kinetic energy. And where is the KE max? Well, that's easy. At the bottom, it's swinging as fast as possible. That's how a pendulum system works, and that's the conservation of energy. Energy is always conserved, gang. See you in class.